Welcome to this NPTEL lecture on principles and techniques of modern radar systems. We were discussing tracking radar. Out of that, in the last class, last two classes I think we have seen the monopulse technique. We are continuing that discussion. We have seen the angle detection. For that, a ratio, monopulse ratio D by S, complex ratio, that is useful, that gives directly the angle thing. Now, we will see the implementation of that, and so we will first see the block diagram of the monopulse system. So, it is called functional block diagram. Functional block diagram of monopulse radar. So, we have a transmitter . Now, that transmitter gives the signal to the duplexer. So, the duplexer, you see that it should have gone to the antenna in normal pulse radars, but in case of monopulse, it actually passes through a microwave combining network. What is this? We will later see, but what happens now? This duplexer, that actually, or this side, it gets produced the actually this signal from this network, it goes to the 4 feed horns. So, we are calling them actually this side I can say A, B, C and D. These are the 4 feed horns. So, it is going from here. So, also to those 4 horns, actually from them this microwave wave also produces a sum pattern, and that sum pattern I should sorry. So, A, B, C, D, and let me call this one as sum pattern. So, that sum pattern goes to the antenna. So, you can think like this, that this sum pattern going, actually it is not a separate entity, this ABCD, but this network makes a sum and that is produced. They are equally excited ABCD from the transmitter via duplexer, and that produces in the circuitry a sum. We will see that microwave combining network will be able to produce a sum. So, that sum is transmitted. Now, while receiving from the target, the echo is received, that echo is ABCD. So, we can say that this ABCD, they are the cluster of 4 feed horns. So, these horns will receive that signal that we are calling ABCD, that we are putting to this network, and here also then that S will come, whatever has been received from that S, what has been transmitted, that S is I am writing here also. So, duplexer, then it will go to the receiver. This receiver we call it sum receiver, and also this microwave combining network ABCD has been input to them. It will give us also a circuitry called another receiver, traverse difference receiver. Also there will be an elevation difference receiver. So, 3 receivers we have. One is sum receiver, only sum receiver is through the duplexer, because sum is transmitted. These are received ones. So, traverse difference receiver, elevation difference receiver. Now, this thing needs to be given to 2 processors. One is called traverse monopulse processor, and it output will be the traverse angle. So, traverse angle. Similarly, there will be also elevation monopulse processor. So, its output will be elevation angle, and also to have this processor, this sum receiver output, that also sum receiver output also to be fed here, and sum receiver output also needs to be put at the input of this elevation monopulse processor, then only they will be able to process. And this sum receiver, after this, that means angular thing is detected, then it goes for detection and range, etc. Those things are performed. And what is done with this? Now, we have got this 2 angle thing. So, this if required, that you want to align the radar, monopulse radar, to the direction of the target, because that is the job of tracking, then it is given to for error correction error correction. This is actually optional part, and also still you see we have got traverse and a thing, but actual thing is the elevation and azimuth. So, what is done? These 2 things are taken, and here is a block to which this is So, what is this block? This is coordinate transformation. So, it gives you the elevation and azimuth, and then there is another block to which this is given, that the antenna drive servos. So, servo will control that mechanical drive. Okay. So, this is now given to the drive motors, servo motors, drive motors. Drive arrangement, you can write drive arrangement. So, this is a now main you see that now we will be focusing on this microwave combining network, that how from the received squint beam voltages I can produce the traverse angle and elevation angle. Actually, the heart of that will be that monopulse ratio d by s. We will find out the mathematics, we will find out the circuitry, everything. But before that, I want to say thing which is very important, many times we so we have written the monopulse ratio. We have seen monopulse ratio is that d by s, but actually it is a complex quantity phasor. Why it is complex? I recall that the concept of complex envelope. So, if we have a RF voltage, sinusoidal voltage, because we have carrier A cos omega t plus phi. So, we in phasor notation we write it as V t, where V t is A e to the power j omega t plus phi. So, we know that to get the real signal V t, we need to take the real part of V t. That means, we know that we can work conveniently with this, because if there are multiplications, actually in modulation etcetera, or in AC circuits, you have seen this phasor concept. Now, if you have any operation, particularly multiplication, division type of operation, then phasors are handy, because multiplication, division of e to the power something is convenient compared to cos and sin. So, that is why we do there, but when we come back, we again make that V t is nothing but real part of V t. That is fine. So, we know that our real signal is, or actually all signals are real. So, real signal is nothing but the real part of the complex signal or phasor signal. Now, what happens that if I have a ratio, then we need some caution that we need one caution, that is, we have seen that the ratio d by s, I tell you these are RF voltages and the phase is important. So, actually we will the radar also, while analyzing, we will take that these are the phasor ratios. So, actual d by s is what? Actual d by s is real part of this phasor. Now, while doing that, actually I want to tell you, probably you know it, but still many times that students make a mistake, that this is not real D by real S. If you do that, this will be wrong. That means, individually you cannot make that, okay, this means real D by real S. No, it is you up till you make this ratio final calculation, you keep it as phasor, then only the whole thing that you can make real part. Now, here also there is a caution, you see that at RF level we are making this RF signal where a monopulse ratio. Now, I am saying that this is a actually the voltages are RF voltages, but for analysis and they are band pass signal. So, we represent them by complex envelope and makes this as a complex quantity, and actual thing is real part of this quantity, provided you see we are in the receiver. After I am getting the signal in the receiver, there is a IF mixer. So, in the mixer this phase information should be preserved. So, this receiver of the monopulse receiver should preserve that. Now, there is a concept that this the complex envelope, remains, this can be proved, remains unchanged when we make RF to IF conversion. But there is a catch, actually generally in communication this catch always is not mentioned, that this is true, remains unchanged, provided LO frequency, local oscillator frequency is below RF frequency. And if it is not, if LO is, because I can make LO also greater than RF also, then the phase of complex envelope gets inverted. So, in that case, when finally taking, you will have to take the imaginary part of the complex ratio to get the actual D by S ratio. So, remember this. Also, there is another thing that I will now take the help of a diagram. Actually, in the receiver, the reference phase, let us say that oscillator reference phase is like this, and the sum pattern in the phasor diagram, sum pattern is, let us say its angle is delta S, and I think green. So, let us say the difference pattern, its angle is delta D. Delta D, delta S. So, when we will form the ratio D by S, what is this phasor D by S? Now, separately what is actually phasor D? I can write, this is the magnitude part, the length of this arrow, and e to the power j delta d. What is S? S e to the power j delta s. So, what will be d by s? It will be d by s e to the power j delta d minus delta s, which what is it? It is actually this let me call delta. So, this is d by s e to the power j delta. Okay. So, actually this part contains all the information, and now we will prove various things that this, if this reference oscillator that drifts, you see if this reference oscillator drifts, what we get? So, I will see a concept that, because previously I have mentioned that d by s ratio is invariant to oscillator drift. That I will prove now. Let oscillator phase drifts by delta, capital delta. So, I can draw the reference diagram again, or in that diagram. So, now I will have to take the this is now delta, that means reference has drifted. So, we can now say that this is the reference, and we will say all this with respect to reference, all these quantities will change and they will be called that new delta. So, I will call that. So, now our S has become S dashed and D has become D dashed. So, what is D dashed, or I can say S has become S dash, D has become D dash. What is D dash? It is, as before, the magnitude will not change, but this is e to the power j delta d plus delta. This is S dashed. So, S e to the power j delta S plus delta. So, their values have changed, but you see what is happening to d dashed by S dashed. So, this is d by S e to the power j delta as before. So, it proves that oscillator phase does not change. Also, you see that actually what is the real d by s ratio? Any time what is d by s? D by s is this, then if we have the real part, that means our LO is less than a cos of the angle delta, is not it? This is the actual scenario. Now, this cos delta will come if we treat everything as a complex envelope, that means at the RF level, if we RF or IF level, but if we go throw away the phase, we only get that cos, and that will change the value, and that will make the measurement erroneous. So, this you should remember. Now, some radars, they also what they do, that they have the receiver chain as IQ things. So, what they do, that I will come there, that this thing, that some radars in the receiver there have that in phase and quadrature components. So, there this ratio will change, but the concept will not change. I will also mention that suppose in the receiver, so I will say that IQ processing. So, receiver is IQ based receiver, actually most of the modern digital receivers are like this. So, this concept also should be seen. What is DI? Actual DI is D cos delta D, and let us call it real part of D. Similarly, DQ, it is D sin delta D, that is imaginary part of D. Similarly, what is SI? S cos delta S is equal to real S, all respect to our that diagram, phasor diagram. SQ is S sin delta S, let me call it imaginary part of S. So, what is D by S ratio? D by S ratio I can write as real D plus J imaginary D divided by real S plus J imaginary S. So, that is I can write DI plus J DQ by SI plus J SQ. So, this D by S ratio, now I can make it DI plus J DQ into SI minus J SQ, and here SI square plus SQ square. So, this will be DI SI plus DQ SQ plus J DQ SI minus DI SQ divided by SI square plus SQ square. So, if your LO frequency is less than RF frequency, you will take the real part. So, what is your D by S ratio? D by S ratio will be DI SI plus DQ SQ by SI square plus SQ square. So, it is not simply the DI by SI or something, So, this is your actual ratio. Now, actually we will show that if you throw away that, then you are not, that means we will prove actually in the next class we will start with this, that you cannot, we are not permitted, suppose we are having that LO is less than the RF frequency. So, we are interested in the real part, but we cannot throw away the imaginary part before we finish our processing. So, that will prove mathematically, and then we will go to the thing. This concept actually is known, but I am a thing that actually my d by s ratio, since it is a complex ratio, in real terms it is d by s cos delta. So, this cos part actually makes the measurement precious. If we throw away this cos part, there will be errors. Similarly, all these are required to make the measurement of d by s ratio precious. This should be kept in mind while having or designing a monopulse radar. Thank you.